In this session, we're going to talk about the Fourier series, which is a means of approximating other functions in terms of sine and cos functions of varying frequency. So it looks like we've got a lot of maths up on the board. It looks quite intimidating, I admit. However, all that you're doing is taking this top function up here, and you're trying to find these three coefficients, a0, an, and bn. Okay? So this first term out here is just an offset, so how high are we up or down the y-axis? This an function tells us how much each contribution from each of the various frequencies of cos we're going to use. And bn does the same thing, but for the sine function. Okay? And Joseph Fourier, the man who discovered this principle, has derived equations for how we calculate each of those three things. You might see other descriptions, other sets of equations to describe the Fourier series. There are many other equivalent descriptions. This is the one that we're going to use today. And again, even within these definitions, you've got an integral of a product of two different functions. It can look a bit intimidating, but it's not. It's all doing things that you've already covered in your basic calculus topics. So very often, if you're looking at a function, you need to think about, well, is there any way that I can save time by not working through every single step, by knowing in advance whether this thing is going to perhaps not contain any causes or not contain any sines or perhaps no offset. And the way you do that is by checking to see whether your function is even or odd or neither or both. So even functions have this property where f of x is equal to minus f of x. So they are a mirror across the y-axis. So some even functions, for example, would look like this. Okay, that's an even function there. It's another even function. Got perhaps an even function here. And you can see that in all cases, they're a mirror across the y-axis. If your function was even, it would only contain contributions from the cos term and possibly the offset term. Okay? But if you think about it, your sine function, we'll put them up here, so cos x looks like this. We'll do some axes. So cos looks like this, which is, of course, itself an even function, and sine looks like this. And we're going to have to bear these in mind all the way through the process. What do our two functions look like? Okay, and sine, of course, looks like this, which is an odd function. Okay, so imagine if we're trying to approximate an even function. There's no way that it can include any contributions from the sine terms because the sine terms are themselves odd. So you'd always end up with one side of your y-axis being different from the other, which would not sit well with this definition of even functions. And for completeness, an odd function has the property f of x now equals minus f of minus x, which means your functions will look like this. So here is a simple odd function. Here is another one. And all these functions can be rotated around. So let's not forget functions that do something like this, if it was drawn a bit better. Okay, so all these functions, if you twisted them 180 degrees around the origin, they would look exactly the same, whereas these ones are mirrors across the vertical axis. So we understand even and odd now. What we're going to do is take the example of perhaps the simplest example for Fourier series analysis, which is going to be the function f of x in the range f of x equals x, very simple function, f of x equals x, straight diagonal line, in the range minus pi to pi. Okay, f of x in the range minus pi to pi. And this is a periodic function, which means outside of this domain here, we are going to just repeat exactly the same shape again and again, which means it's going to look something like this. Okay, so we'll get our function. It's going to be a diagonal line and then it's going to come down again. So here's our basis, minus pi to pi. Okay, but outside of that domain, it's just going to do exactly the same thing again. And of course back here as well. Right? Now, if this is the function f of x equals x, if x equals pi, then clearly f of x must equal pi as well. So this is going to be pi, oops, and this down here is going to be minus pi. Okay? And what we're trying to do is use this set of equations to reconstruct our function using cos and sine functions, right? So the first thing we do, as I said, is think, is this an odd function, an even function, neither, or both? Well, this thing, just in the domain of interest, is clearly not even. It's not a mirror image of itself around the vertical axis, but it is odd. If you spin this thing round 180 degrees, it would look exactly the same. So if this thing is odd, if your function is odd, it actually means that none of your cos terms can have any impact on it, okay? It can't have any of these even terms, which means that all of your an coefficients are going to be 0. So there's no an, therefore an equals 0. And that includes a0, which is a special case of an, okay? So it's odd, therefore all an equals 0. So that means already we've cut down the work a lot. Already we are just looking for these bn coefficients. So let's try and find the first one. Okay, so if we say, well, what's this L thing? I haven't explained this. So L is half the period. So our function has got a period from minus pi to pi, which means its period equals 2 pi. Therefore, L just equals 1 pi, okay? So L equals 1 pi. So now we can sub all that in and try and find B1. Let's try and find B1, our first coefficient. B1 equals 1 over pi times the integral from minus pi to pi of our function f of x, which is just x, times sine of n pi x over L dx. Okay? That's all we have to do. We're going to evaluate this thing, and it will give us a number, and then we know B1. Okay, so how do we evaluate this thing? Well, we've got to integrate the product of two functions. How do we do that? Okay, if you can't remember integration by parts, just remember that it's actually just the product rule in disguise. I'll just show you that briefly. If you remember, the product rule is when you're finding the differential of u times v, you get u dv plus v du. Well, actually, you can just move this thing over to the other side, and you now get the integral of u dv equals uv minus v du, and that's an integral there as well. Okay? So this is what we call integration by parts. Integral of u dv equals uv minus the integral of v du, and all you've got to do now is choose which one of your two functions you want to be u and which one you would like to be dv. Well, the general rule is you pick the one that's going to be u if it will disappear eventually through differentiation, okay? Because you only ever differentiate u. And of course, x is going to disappear, whereas it doesn't matter how many times you integrate or differentiate the sine function, it's just going to stay around. It's just going to hang around. So we'll leave that definition up there for a second. Okay, so let's start. So B1 equals 1 over pi, and we're going to have lots of brackets here. Okay, so be careful not to get confused. Equals the integral. So if this thing is our u, and this thing is our dv, so It's saying we want u times v. Well, v is the integral of dv. So sine is going to integrate to minus cos. Okay, so it's going to integrate to minus cos. What I didn't do is sub in this L term here. We know that L equals pi, which means that this thing is just n pi x over pi, so the pi's cancel. So it's just sine of nx, okay? We need to have x, which is u, so we've got some more brackets, x times the integral of this thing, which is just going to be minus cos of nx divided by n. And of course, we're finding b1. So actually, n is just 1 in this case. Okay, so I can leave that as it is. So here we go, shut the brackets off here, and that's from minus pi to pi. So we've done our first term, our uv. Now we have to do minus the integral from minus pi to pi of v du. So v du, we've already found v, it's cos x over 1, minus cos x over 1. So minus cos x over 1, so that becomes a plus. So cos x, and we're multiplying it by du, and the differential of x is just 1, and this thing is therefore dx. Close the big brackets off. Right, let's go through again and simplify. So 1 over pi, and we've now got to sub this thing in. So we say, okay, what is minus pi cos of pi? So our cos function looks like this. Here is pi here. Here's pi here on our sine function. So cos of pi is just minus 1. Okay, minus x, where x is minus pi, so that's just plus pi. And cos of minus pi is also minus 1. Minus 1. Okay, lots of brackets, lots of minus signs, lots of opportunity to lose marks in an exam by forgetting them. Okay, I will do my best. Okay, so that's superfluous. Okay, so now we want to integrate the cos function. Okay, when we integrate cos, we get sine. So we've now got plus sine x evaluated between minus pi and pi. Okay, the sine function at pi is 0 and at minus pi is also 0. So this thing is just going to disappear. Okay? So we're left with b1 is going to equal 1 over pi, and then we have to work out what's going on in this bracket. So we've got minus pi times minus 1 is plus pi, and minus pi times minus 1 is plus pi, so we've got 2 pi. b1 equals 2 pi over pi, b1 equals 2. Right, so that is the first term. Now you might be thinking, oh God, how many of these are we going to work through? Well, actually, what we're going to move on to now, and we'll store this down here maybe, b1 equals 2, is we're going to try and integrate this thing again, but this time leaving the n in place. So keeping it nice and general. So I'm going to write the integration by parts up here. Integral of u dv equals uv minus the integral of v du. Okay, leave that up as a useful tool. Right, so we found our first coefficient. Let's just find the nth coefficient. Then we can write a general expression down that is basically this thing, but subbed in for our an term. So we can say, okay, we've got bn equals 1 over pi, we're looking at this function here, 1 over pi, the integral from minus pi to pi of f of x, which is still just x, times sine of n pi x over L, which is just pi, so just nx dx. We're going to integrate this thing, leaving the n in. Okay, it's going to look very much the same as what we just did. So we can do it nice and quickly, hopefully. Bn equals 1 over pi, again, big brackets. So our first term is going to be this uv thing. So we're going to get minus x over n, because of course sine nx differentiates to 1 over n, minus 1 over n cos nx, cos nx, minus the integral of minus cos it, so it becomes a plus again. You get this 1 over n term, and then we've got the cos in here, so cos nx dx. Okay, and then close the big brackets here. We work it through to the next step, so bn equals 1 over pi, big brackets, and this is of course between minus pi and pi. We work it through again. So what's happening inside this bracket? So we've got a minus pi over n times cos n pi. So if we look at our cos function up here, when cos is a multiple of pi, because n's just an integer, so it can either be 1 pi, 2 pi, 3 pi, 4 pi. What does that mean? Well, when it's 1 pi, it's minus 1. When it's 2 pi, it's plus 1. And it will just keep alternating like that forever. So minus 1 plus 1, minus 1 plus 1. So it's actually, a quick way of writing this is minus 1 to the power of n. So when n is 1, this thing's minus 1, that's correct. When n is 2, it becomes plus 1 again. Okay. Minus, and now we've got minus minus pi, so that's just pi over n, and then exactly the same thing again, because of course, because cos is an even function, it's symmetrical about the vertical axis, so you just get exactly the same thing, minus 1 to the power of n. Okay, that's this first term done. What about this thing over here? We're just going to have to integrate cos again, as we did before, so we're going to get plus 1 over n squared. This time we've got 1 over n times 1 over n, and now we get a sine nx term here between pi and minus pi. And thankfully, just like last time, our sine term at any integer multiple of pi, it's just going to go 0, 0, 0, 0, 0. So this term is just going to disappear again. Right. So we've now got bn equals 1 over pi. What's going on in this big mess here? So we've got, we've essentially got minus pi over n times this thing twice. So we end up with, here's 1, and this minus sign applies to this whole bracket, so here's another one. So we get minus 2 pi over n times minus 1 to the power of n. Okay, we're nearly there. And now we can say, actually, this pi is going to cancel with this pi. So we now get minus 2 over n minus 1 to the power of n. And we can even make it perhaps slightly neater than that, which is that we say, okay, minus 1 to the power of n is minus 1 multiplied by minus 1 n times. So minus 1 times minus 1 times minus 1. Well, we've already got an extra minus 1 hanging out here because our first term is negative. So that's timesing it by n plus 1 of minus 1. So we can write a slightly neater form and say, well, bn equals 2 over n minus 1 to the power of n plus 1. If you don't know, if you don't understand what's going on here, think about having an x times x to the power of 3. Well, that's just x to the power of 4, right? You just add 1 to the index, and that accounts for the extra multiplication. So we now have our general expression for our bn coefficient. Okay? So we can get rid of all this working. And now we can start to have a think about a general expression. So we can say that our approximation, GM, is going to equal the sum from n equals 1 to m of, we've got our Bn here, of 2 over n minus 1 to the power of n plus 1 sine nx. And that's it. That's the whole thing. Now, what on earth is that going to look like? Well, all it is adding up lots of sines of different frequency. Okay? So we'll do the first one on top of our current axes. And the first one has got a coefficient of, when n equals 1, you get 2 divided by 1, so just 2, and minus 1 to the power of n plus 1 is 2, so just 2, as we've already found out, b1 equals 2. So if our function usually comes up to pi, okay, 2 is going to be somewhere here, and minus 2 is going to be somewhere here. Okay, so it's just the sine function multiplied by 2, which is going to look like this. Okay, and coming down here. Okay, now clearly doesn't look much like it yet, but at least I hope you can see that it's kind of in the right direction in a way that a cos function never could be. Okay, when the green is coming up and positive, the red function is up and positive. When it's going down, it's down. Okay, so as we add more and more terms to this thing, it's going to start to look more and more like our function. And eventually, as m is getting very large, we'll have a representation that looks like this. Okay, which is near the discontinuity, it's still quite messy. But along these long straight regions, it becomes very much like the function. And this is called Gibbs ringing. And basically, as you can see, our function has got discontinuities. So unlike the Taylor series, which usually totally falls apart around discontinuities, the Fourier series can handle them, although for a finite number of terms, you do get this very strong effect of the very high frequency oscillations of your function still coming out, even though you've got many terms to cancel each other together. So there are some functions for which, when m goes to infinity, our approximation becomes an exact equality. But in many cases, you will use the Fourier series to approximate functions, especially if you are, for example, storing images in a computer. And this is how, or very similar to how, the JPEG, if you've ever used a JPEG file, this is how JPEGs compress their data by saying, okay, rather than storing the value of every single pixel, what I'm going to do is reimagine my image made up of loads and loads of cosine functions. And then I'm going to say, what are the coefficients in front of each of the frequencies? And depending on how much space you want to use up in your computer, you will use a finite number of frequencies. So you won't use all the possible frequencies, but you use the lower ones and build your way up, depending on how much memory you want to use. And that's why, for example, when you store images perhaps with very sharp outlines to text, which would have the equivalent of strong discontinuities, so if you've got a letter with a very sharp edge, if you don't use high enough frequency terms, you end up with a kind of blurring. So when you zoom into a JPEG, it's like the letters have all blurred out around the edges. And that's because you've used lower frequency contributions of the Fourier series. So other than that, it's also used used in nature by your actual ears. So your ears, rather than constantly sending your brain what value the pressure wave is at, so if you imagine a sound wave coming into your brain, your ears are not saying pressure, 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 pressure. What they're doing is they've got a long canal, and within the canal, at various different points, are hairs or little tiny features of your ear that will resonate when they are exposed to a certain frequency. And so your brain just says, there's this much of this frequency, or there's this much of this frequency. And so it gets the frequency information rather than the time information. And that's it for an introduction to the Fourier series. See you next time.